Hello IB1 students, welcome to my first video lesson recorded specially to you. I recorded few video lessons to different groups and feedback is positive. Students say that it's maybe not ideal form, but very good form of presenting new material. Okay, I hope that you are prepared. Prepared means that you have physics notebook, you have pen, pencil, a ruler, eventually calculator. If not, please stop video for a few minutes now. You can turn it when you will be ready. So organize your physics notebook, something to writing, and let's start our topic. Okay, so topic is ideal gas. Okay, you have to do a notes. I will be explaining the best as I can. Okay, point number one, write or mole. 1 mole. Okay, what is a mole? I hope that you know that this is the base unit, standard unit, and it expresses amount of substance. Okay, so the meaning of 1 mole is the same as meaning of 1000 or 12 or billion. Is amount, a number, a specific number. Okay, but this number has a definition. 1 mole is defined as amount of substance containing the same number of molecules as 12 grams of carbon 12. Okay, so this is definition. So let's imagine that you have sample of pure carbon 12 element, and this sample has a mass of 12 grams. You will count atoms in this sample. The number will be corresponding with 1 mole. It will be not billion, it will be not 1000, it will be not 12, it will be 1 mole. Okay? And 1 mole is a kind of a constant number. So 1 mole is amount of carbon 12 atoms in 12 grams of carbon 12. But as you know, different atoms may have different mass. Okay, so we have heavier atoms than carbon 12 and smaller atoms or less massive atoms than carbon 12. But definition refers to the carbon 12. So 1 mole is the same, is the amount of particles as amount of particles in 12 grams of carbon 12. This is definition. Okay, but of course, if you have lighter atom like helium, I hope that you know that mass number of helium is 4, then you need only 4 grams of helium. Why? Because helium atom is 3 times less massive than carbon 12 atom, which means that mass of 1 mole will be 3 times less. Okay, 1 mole is also the same as amount of substance in 1 gram of hydrogen 1. Hydrogen 1 is 4 times less massive than helium because its mass number is 4 times less. So mass of 1 mole is 4 times less. Clear? Okay, 1 mole is also the same amount of substance as, let's say, 235 grams of uranium 235. Uranium is heavier element, much more heavier than others, around 235 times more heavier than hydrogen. So mass of the same number of atoms must be 235 times bigger. So this is why 1 mole of uranium 235 has a mass of 235 grams. But remember, definition refers to carbon 12. Okay? Please copy this. Stop video for a moment. When you'll be ready, turn it. Again, I'm going to talk about point number 2, Avogadro constant. Okay, so what is Avogadro constant? Avogadro constant is something like numerical representation of 1 mole. You can imagine 1 billion, yes? 1 billion is a number. The same as you can imagine 1000. You can count to 1000. The same you can count to 12, yes? But 1 mole is much more bigger number. 1 mole contains the same number of particles as 12 grams of carbon 12, and it corresponds with the number which is known as an Avogadro constant. Is it clear? So you can say that 1 mole contains Avogadro constant, the symbol of Avogadro constant is n with index of A of molecules. And what is this number? Avogadro constant was found experimentally by scientists, and they estimated that Avogadro constant is 6.02 times 10 to the power of 23. So huge number compared with my examples like 12,000 or 1 billion. Avogadro constant you can find in your data booklet. It's here, the first number. You can see 6.02 times 10 to the power of 23. Described as Avogadro constant, symbol is Na. Okay? So again, if you have 6.02 times 10 to the power of 23, then amount is 1 mole. Is it clear? Okay, so let's imagine a simple example. Let's imagine that you have a sample containing, let's say, 8.00 times 10 to the power of 23 of molecules. Knowing that Avogadro constant is equal to 6.02 times 10 to the power of 23, find number of moles of this substance. A symbol of number of moles is N, okay? Number of moles. Okay, so how to do this? We know that 1 mole contains the same amount of molecules as Avogadro constant, which is given 6.02 times 10 to the power of 23. And we don't know how many moles corresponds with number of 8.00 times 10 to the power of 23 of molecules. So by using simple proportion, you can find it. Yes, you have to divide 8 by 6.02. I have my calculator, GDC. Yeah, I'm turning it on. Okay, so you have to you have to divide 8.00 times 10 to the power of 23 divided by 6.02 times 10 to the power of 23. And you know what? Unfortunately, my calculator stopped working. Okay, I have different calculator here. 8 divided by 6.02, which is 1.33. In 3 significant digits, 1.33 of moles. Okay? So what is the relation between number of molecules, Avogadro constant, and number of moles? Number of moles is always given by number of molecules divided by Avogadro constant. Write this example plus this equation because it's your first equation today. Avogadro constant, and this is number of molecules. And this is number of moles. Okay, I hope it's simple. Is it clear? Okay, there is one more quantity related with this introduction to ideal gas. Okay, so point number 3, molar mass. Okay, molar mass, I'm going to use symbol of mu, the same as micro, but molar mass is a quantity, micro is a prefix. The same symbol, but completely different meaning. So what do you think, what is a molar mass? It's simple. Molar mass is mass of 1 mole. Okay, so let's take this carbon-12 as example. So what is a molar mass of carbon-12? Molar mass of carbon-12 is 12. Why? Because you need 12 grams, or 12 grams per mole, yes? You need 12 grams of carbon-12 to make the same amount of particles as is in Avogadro constant. Tell me, what is a molar mass of helium-4? Molar mass of helium-4 must be equal to 4 grams per mole, because 4 grams of helium-4 is needed to obtain the same amount of molecules as Avogadro constant, which represents 1 mole. Is it clear? Okay, we have 3 terms. First, 1 mole, which is defined by amount of carbon-12. Second, Avogadro constant, which is let's say numerical representation of 1 mole, and molar mass, which is mass of 1 mole. Okay? And very important unit of mass in this chapter is unified atomic mass. So number 4, you have this in your data booklet also. This is this unified atomic mass unit. Unified atomic mass unit. Okay, 1U. Okay, unified atomic mass unit is defined also by carbon 12, and definition says that one unified atomic mass unit, so 1U, okay, is exactly 1/12 of mass of carbon 12 atom. Okay, so if you have carbon 12 atom of a given mass, and 1/12 of this mass is exactly 1 unit. Is it clear? Okay, so if we recalculate from unified atomic masses, so from units to kilograms, then we can obtain a relation that 1 unit is exactly the same as, you have this in your data booklet, 1.661 times 10 to the power of minus 27 of kilograms. Okay? So please copy these 4 points to your notebook, stop video for a moment. When you will be ready, turn it on again, and next I'm going to conclude this beginning of this chapter. Okay, so short revision. We're talking about 1 mole. Yeah, is defined as amount of substance containing the same amount of molecules as 12 grams of carbon 12. We are talking about Avogadro constant, which is numerical representation of 1 mole, and it's 6.02 times 10 to the power of 23. This number is given in your data booklet. Okay. We were talking about molar mass, okay, which is mass of 1 mole, and it depends on the element, it depends on the atom. Okay, and we were talking also about unified atomic mass, which is also defined by carbon 12, and 1U is 1/12 of 1 atom of carbon 12, which corresponds with number of 1.661 times 10 to the power of minus 27 of kilograms. Okay? Okay, so ready for next point number 5. Okay, number 5, we have to review what the pressure is. Okay, I hope you remember pressure, of course measured in pascals from your middle school. I told you that pressure is defined as force over area, but it is middle school definition. Now a little bit advanced definition. What if you have surface area in the form of, I don't know, plate, and force which acts not perpendicularly to the surface area? Okay, let's imagine that this is the angle alpha between force and a line which is perpendicular to the surface area. In this case, you have to take only component of force which is perpendicular to this surface. Okay, which function links this F? Let's use symbol of 2 lines perpendicular. Okay, with F, it's a cosine. Cosine of the angle is F perpendicular over F, so F perpendicular is equal to F times cosine of the angle. So in this definition we have to add sine perpendicular, or you have to write that this is the force times cosine of the angle between direction of force in direction which is perpendicular to the surface area divided by this surface area. Okay, and of course pressure, the unit of pressure is 1 Pascal. Okay, 1 Pascal is when force is perpendicular force is equal to 1 Newton and acts on area which is equal to 1 meter squared, and of course is a low pressure. Let's imagine 1 Newton, so the weight of 100 grams. which is placed on the area of 1 meter per 1 meter. Is very, very, very small pressure. Okay? So now after this introduction, so after 1 mole, Avogadro constant, molar mass, 1 unit, and pressure, we can talk about ideal gas. What is an ideal gas? Ideal gas is a kind of model. I hope that you see difference between the micro world of molecules and macro world, the world which we're living. Okay, so in the micro world we have individual molecules, and these molecules move, so have masses, velocity or momenta. Yes, these molecules interact with one with another or with walls on the container in which are stored. Yeah, and these molecules occupy some space. Okay, these molecules have speeds, but we cannot measure velocity or energy. We cannot measure these quantities of individual molecules because, as you know, 12 grams of carbon-12 contains 6.02 times 10 to the power of 23 molecules, which means that in the room you are sitting now, you have billions of molecules. Okay, so it's impossible to write equation for each individual molecule and calculate what will happen with this molecule in the next few seconds. Okay, so in other hand we have a macro world. Okay, world in which we are living. Okay, and in this world we have another properties which are very similar to the micro properties, like temperature. Okay, temperature in macro scale is something similar to kinetic energy of molecules in micro scale. Is it clear? Oh, second quantity, like force. Okay, force in which single molecule acts with the wall of the container in which it's stored, can be represented by pressure in macro world. So it's something like equivalent. Okay, and here space between molecules or distance between molecules or amount of molecules in unit volume can be represented by volume, another quantity which is easy to measure in macro world. Okay, so scientists try to describe something which is very small and practically not measurable by something which can be understood by others, which is related with these quantities like temperature, pressure, and volume. Okay, and ideal gas is a kind of model which translates this word into this word. Okay, but there is a word ideal. What does it mean? It means that we have a lot of simplifications. Okay, so write point number, I don't know, it's 6 or 5. So next point, 1, 2, 3, 4, 5. Point number 5. Probably it's point number 5. Okay, so let's write ideal molecular model of an ideal gas. Okay, so what is special in term ideal gas? Okay, in this model, yeah, we have molecules which can be represented by points. Okay, so molecules are point masses. What does it mean? It means that volume of the molecule is negligibly small compared with the volume with the distance between molecules. Okay, or let's imagine that molecules do not move. What is the volume of finite number of molecules? The volume must be equal to 0. Okay, so molecules are point masses means that size of the molecules is negligibly small compared with distance between molecules, okay? Compared with distance between molecules. Okay, second. Molecules move in random motion, molecules move randomly and occasionally collide, okay? So molecules move randomly and sometimes collide. Okay, so molecules in ideal gas model behave as, balls on the pool table, okay? Move and collide, move and collide, so we can use simple Newtonian mechanics. And of course, you must know that these collisions are perfectly elastic. What does it mean? It means that there is no energy lost during collisions, okay? So no energy lost during collisions is very, very, very important, okay? And last point of ideal gas is that molecules do not interact one with another, of course, except collisions. And during collisions there must be interaction, yes? So molecules do not interact. We can write except collisions. Okay, and what does it mean? In other words, it means that molecules, there is no potential energy between molecules. No potential energy, molecules do not attract, do not interact, do not repel one of another. So what is difference between a real and ideal gas? Real gas can be described in a very, very similar way as ideal gas if the pressure is very, very, very low. Okay, in very low pressure. So again, what is ideal gas? It's a kind of model. This is something which describes behavior of molecules. When molecules are point masses, when molecules move randomly and collide, and when molecules do not interact, so there is no potential energy. If you have a gas which behaves as this description, it can be known as an ideal gas. Okay? So before I will finish this lesson, let's do a few exercises at home. Your homework is open your Tsokos on page number 126. In 126, 127 and 128 you have description of this that I was talking about. Okay? So next lesson we'll be talking about Clapeyron's equation, about pressure volume law, about volume temperature law, and about Charles law. Okay, and about pressure temperature law, and we'll conclude this by Clapeyron's equation, so equation of state of an ideal gas. But please open your homework. Please open your Tsokos on page number this one, so 140. Okay, page number 140, and do exercise 13, 14, 15, 16, and okay, enough. 13, 14, 15, 16. Exercise 13, 14, 15, and 16. Your Tsokos. Page number, it was 140. Okay, I hope you like this lesson. I'm going to record and send to you and share to you one lesson in each physics day. So for standard level, minimum 2 lessons per week. For higher level, minimum 3 lessons per week. Okay, do your homework, learn physics, and see you next day. Next lesson we have probably tomorrow, yeah? Okay, see you, bye.